Morning, everyone. It's Dan Sandig from the Institute for Catastrophic Loss Reduction. Thanks very much for joining us for the last Friday Forum of this season. Today we have Adam Blazejowski from Western University, who's going to talk about his work on hail damage to automobiles. Adam is an undergraduate in the Department of Civil and Environmental Engineering and is a research student with Professor Greg Kopp. And he's been doing a number of very interesting projects over the past couple of summers. This, I understand, was his project from last summer. So it'll be very interesting to hear more about his work and possibly have him back in the future to talk about his other projects. Just a reminder to ask questions using the Q&A function in the webinar, and we'll be collecting all the questions throughout the presentation and having a discussion at the end. This is the last webinar until September. We haven't quite sorted out the schedule yet, but watch your inboxes, and I believe we have somebody scheduled for September 21st, but you'll get the notice pretty soon from Tracy Waddington. And I also understand that this webinar, this presentation might be a little bit shorter today, so we might not go until 11:30, but we'll see how it goes. So with this, I'll pass it over to Adam.
Well, thank you, Dan, for the introduction. So hello, everyone, and thank you for joining me this morning. And I'd like to start my presentation just by showing you a picture of what typical hail damage to automobiles looks like. And just so we have a visualization of what I mean by hail damage. Okay, so like Dan said, my name is Adam Blazejowski. I'm an undergraduate research student at Western University. And today I'll be presenting my project I did last summer titled Hail Impacts on Automobiles. So firstly, I'd like to put this, the hail problem into some numbers. In Texas, the costliest storm actually in their history claimed $560 million in damages to automobiles alone. And going north to Alberta, the costliest storm of 2015 claimed $230 million in damages. So the hail problem is prevalent anywhere between Texas and Alberta in the central North America. And a less obvious issue with hail damage is the amount of hail claims that are made. So actually, out of all the hail insurance claims, which include damage to agriculture or damage to homes, 34% of those are attributed just to automobiles. And that roughly translates to about 700,000 claims made in 2 years. Now, following any large hailstorm, hail insurance offices are flooded with calls, and it does take a while to sort out, and it's a lot of paperwork and time. So these are two reasons why we want to solve the hail problem. So people have taken this problem into their own hands, and a few ingenious creations have come out onto the market, and they claim that they offer hail protection, but there is no way of telling if they're working or how well they're working. So that's why I believe a standard test method does need to be made in order to qualify these products. And when I first started researching hail damage to automobiles, I realized that there were a lot of related subjects to it, but there wasn't really a central resource for hail damage to automobiles. So I made it my work, my primary goal, to bring together all this information into one central resource. And I set 3 main goals to achieve through my project. The first being to make a background literature review, making the central resource for hail damage to automobiles, but then also providing preliminary impact testing results that people can compare their results to mine and address really any discrepancies that they may find. And I also want to provide recommendations for future projects. So I wanted to really kind of show what what things can be done and what things need to be done in order to advance our knowledge on this subject. And I also included some conclusions from my project and from my testing. So just a quick overview. We're going to start off with the literature review, which is going to cover everything from impact mechanics to hail replication. This is going to sound a little bit like a lecture, but after that, we're going to go into the more interesting stuff of impact testing, which I'm going to cover my calculations and my results from the testing. And finally, we're going to finish off with recommendations and conclusions that I came up with. So starting off with impact mechanics, the central idea behind the physics of the impact is that materials transfer the energy from the impact into deformations such as cracking and denting. Now this is really important to know because different parts of the car do deform differently. For example, the windshield is more likely to chip or crack, but the glass will always stay together since windshields are constructed from two panes of glass with a sheet of polyvinyl in between that holds the glass together. However, if you compare that to the side and rear windows, which are made of tempered glass, which in other words means the glass is cooled really quickly, this type of glass actually shatters and it goes into very small bits of harmless piece of glass. And that's done obviously for safety reasons. However, body panels deform much differently than any type of glass. A body panel will actually physically dent as a way of deforming, and the aesthetic damage is what concerns us because that's what's costing the most money. And when it comes to deforming body panels, specifically metal body panels, there are three modes of deformation. The first one being plastic, where after the impact there's a physical dent left behind on the surface. Then there's an elastic deformation, which means that the body panel will return to its original shape after the impact. And then there's subsurface plastic, which means that it may appear to be an elastic impact, but below the surface of the body panel there is physical or plastic damage. So the mode of deformation can be predicted, and it depends on the material properties of the actual body panel. It also depends on the speed, the velocity, and the mass of the projectile. Or in this case, it's the hailstone. Now, there are already ASTM test methods for hail resistance of windshields, and specifically the ASTM F320 standard describes a way of impacting a windshield by using a air compressor gun. And as you can see on the left there, the gun comes in three parts. The first one being the valve, which screws into a breech, and then the barrel screws in directly into the breech. Now the hailstone doesn't travel in the barrel alone. It's actually enclosed in a sabot, which is kind of like a casing, which protects the hailstone from becoming damaged in the propulsion stages. So once the sabot holding the hailstone exits the barrel, it's designed to come apart and just leave the hailstone or ice ball flying by itself and hitting the windshield. And there's actually a specific impact pattern in this test method that requires the impacts to be made 5.6 inches apart. And this is so that the impact at one location doesn't affect the performance of the windshield at another location. So coming back to the types of deformations, elastic deformations are defined with equations. On the right there, you can see a picture of a sphere coming into contact with a, in this case, it could be a body panel of an automobile. And you can see the circles that are radiating away from the contact center are getting lighter and lighter in shade. And that represents that the stress fields at the point of contact are largest, and they slowly diminish moving away from there. And you can actually find the values of the stress by using equations. And the equation also exists for the vertical displacement of the specimen and how far it would move downwards. And the vertical displacement equations depend on the impactor shape. So the impactor shape can either be a cone, a sphere, or a more of a blunt shape, like a rectangle. And it's really important because it's also interesting that the equations actually assume that the impactor is perfectly rigid. And I'm not sure that this would be the best assumption for hailstones, since the hailstones do deform on impact, and they have air bubbles inside that will compress and deform with the ice. So that should definitely get looked into further. When it comes to plastic deformations, it's not as easy as plugging numbers into an equation. You have to use something called finite element analysis, which basically separates the for example, if we're talking about the hood of a car, it separates the hood of the car into very small elements or little squares across the surface, and then those squares can be solved and they give an equation, and then you get a whole bunch of equations for each bunch of those little elements on the hood of the car. And once you solve those equations, you can figure out how much the hood will deform. And there has been finite element analysis software developed at the University of Waterloo. Now, how do we fix these dents? The modern way of fixing these dents is called paintless dent removal. And this involves getting behind the body panel and trying to force the dent out with various tools. There's also various other tricks that they use, such as heating the surface of the dent to make it more malleable. And it's always done by a PDR specialist that is certified by an organization called Vail Training Solutions. And they actually offer multiple training modules for different trades. And the primary role of the PDR specialist is to estimate the damage, and that cost is actually given through the body shop to the insurance company. And then once the damage is estimated, they help using a hail pricing matrix, which I will show you on the next slide. PDR specialist then repairs it. Now, the PDR specialists do work independently, and they just come to the body shop to perform the work. And I was fortunate enough to meet up with one of the PDR specialists in London, Ontario. And there's actually two of them, one for the north and one for the south. And he gave me a lot of important information that I'm presenting to you today, as well as the hail pricing matrix that I will provide on the next slide. Most cities in Central North America and Southwestern Ontario do have at least one PDR specialist. Unfortunately, I didn't get to see him perform the PDR. I was just a little late, and he just finished up fixing a Mercedes-Benz that was hail damaged in London. So this isn't just a problem in Central North America, it's also in Southwest Ontario, and I'm sure on the East Coast as well. So that's the hail pricing matrix. They're more or less a similar format, although they vary from company to company. But ultimately, the damage does come down to where the dents are located, the part of the car, the amount of dents that are on that part of the car, and then also the average size of the dents, which is just visually estimated by the PDR specialist. It's also interesting to note that any minivan, SUV, or truck is 25% more expensive than a normal car, and aluminum body panels are at 25% as well. Now, PDR isn't always a viable solution. As you can see in some of the boxes, it says CVR, and CVR basically means you have to replace that part of the body panel, and PDR can't be used to fix it. Now I will answer this question. So when I first made an estimate of the damage myself, without using the hail pricing matrix, I should say, I thought it wouldn't cost more than a few $100s, but after using the hail pricing matrix, it turned out to be twice as expensive. So by using the hail pricing matrix, I said those dents look about the size of a quarter on average, and I counted 5175 dents, and I came up with a price tag of $700 just to fix the hood. Now, if you add the roof of the car and say the trunk lid and the fenders, you're looking at easily about $2,000 per car. And then if you look in the background, there seems to be multiple cars, and this was actually taken from a dealership. This damage was at a dealership. So if you're looking at $2,000 for at least 100 cars, it amounts to quite a bit of money. Now, when it comes to fixing windshields, there's only one way, and that involves injecting a resin into the chip or crack. However, this method is very limited. It requires that the chips and cracks be less than the size of a dollar coin and at least 5 centimeters away from the edge of the glass. It's also fairly expensive, coming in at around $100 for a chip or a crack. These numbers I got from a local auto glass repair shop. And I compared this to the cost to replace a van-sized windshield, which is $400. So after a hailstorm, you're most likely going to have more than one chip or crack in the windshield. So the most likely event is that you're just going to have to replace the whole windshield anyway. Now, currently on the market, there are 2 products that offer the alleged hail protection. The first one being from a company called Cover King. And this cover is just simply overlaid on top of the car, as you can see in the top picture there. And it costs $184 US. Then the other product is called the Hail Protector, which is a, it's not permanently on your car, so you have to also take it out and install it. However, this product actually inflates around the car like a balloon. And it actually works on a, it's powered with a pump that plugs into either a battery pack or the car battery or an outlet. And it's also very convenient because the Hail Protector comes with an application for your cell phone. And it actually will give you alerts if there's a anticipated hailstorm in your area. And this product comes in at around $400 US. So hail properties also must be very well understood, just because when we want to replicate hail, it's important we get the hail properties correct so we get realistic results. And just as a general information, hailstones are formed in supercell thunderstorms, and supercell thunderstorms are basically clouds with a strong updraft, downdraft cycle contained within the cloud. And they will actually precede the formation of tornadoes. So actually, wherever you have frequent tornadoes, you also have risk of frequent hailstorms. So that explains why where Tornado Valley is located in Central America, or Central North America, there is also frequent hailstorms in that area as well. And although the first requirement is to have a supercell thunderstorm, the second requirement is for supercooled water to be contained within the cloud. Now, supercooled water is, supercooled water droplets rather, are droplets of water that are suspended in the air that are actually below the freezing temperature of water. And the reason why this can occur is because they are suspended in the air and they haven't come into contact with anything to crystallize. Once they come into contact with a piece of ice or a piece of dust within the cloud, they will immediately crystallize and form ice. However, that contributes to the types of growth. Wet growth occurs when the supercooled water droplet comes into contact with a piece of ice in a part of the cloud that is actually close to 0 degrees or warmer. And when that occurs, the supercooled water droplet will actually envelope around the piece of ice, and any air will escape and it'll freeze as solid ice. And that results in clear ice. Compared with dry growth will occur in a part of the cloud where the temperature is way below freezing, and the supercooled water droplet will freeze immediately on contact with another piece of ice. trapping any air inside. And the air bubbles will actually give the ice an opaque color. Now, as you can see in the bottom there, there's a cross section of a hailstone. Each one of those rings represents one cycle in the supercell thunderstorm cloud. And specifically, the opaque layers represent dry growth cycles, and the clear layers represent wet growth cycles. Now, a lot of work has been done on hailstone properties, namely by Ian Jumanco from the Institute Insurance Institute for Business and Home Safety. And he conducted multiple lab tests and field studies. And one of his field studies was based around the idea of finding out what the shape distribution is. And it turns out that 84% of hailstones he collected from the field were spheroidal, 10% were conical, and 6% were irregular. Now, why is this important? It's important because if you recall, the deformations actually depend on the shape of the impactor. So spheroidal, conical, and irregular shapes have to be tested on automobiles. And in the ASTM F320 test standard, the same one we saw earlier, that's the one for testing windshields, there's also a method outlined for creating injection molded ice balls. In this method, they don't specify what material to make the mold out of. They say you can either 3D print it or mill it out of a piece of metal. However, they do emphasize to use a syringe and fill the cavity within the mold from the bottom up. So you stick the syringe all the way into the bottom of the mold. And the reason why they emphasize that fact is because they require the ice balls well, as the water comes upwards, it forces any air out. So you have only water in the cavity. So when it freezes, you have solid ice and no air bubbles. Now, I'm not sure this is the best way to make ice, just because we saw earlier that many hailstones undergo dry growth, which has air bubbles inside. And that actually results, solid ice results in harder, more durable hailstones that will impart more damage. And Ian Jumanco noticed this in his studies. He noticed that the injection molded hailstones do have a higher hardness than natural hailstones. And that's because they don't have the air content that natural hailstones do. And theoretically, he also says that harder hailstones impart more damage on the specimen because of the reduced air content. Hailstones impact at terminal velocity, which means that they're traveling at a constant speed. And the only way that a hailstone can attain a constant speed is when the drag force that points upwards towards the sky equals the weight force of the hailstone, which is pointing down. Now, I calculated the distances that it would take for various sized hailstones to reach their terminal velocity. And I found that only the 0.5 centimeter hailstone would reach terminal velocity in an 8 meter or less drop. Now, the facility that I was at, I only had 8 meters to work with. So I realized that I basically couldn't do drop tests. And the only other obvious option was to create a air compressed shooter as described in the ASTM F320 test method. However, I decided to not build the shooter just because I felt like it would take too much time out of my summer just to build it, and I really wanted to get into testing. So I decided to to match the kinetic energies of the hail, and the kinetic energy is given by 1/2 times mass times the terminal velocity squared, and that's the impact energy of a hailstone. However, I could match this by increasing the mass of it to a larger ice ball and just dropping it from 8 meters. For an example, a 1.5-inch diameter hailstone impacting at its terminal velocity has the same impact energy as a 2.5-inch diameter hailstone dropped from 8 meters. And being dropped from 8 meters, the hailstone would be traveling at 12.5 meters per second. So I did all my testing. I tried to match the kinetic energies. And here you can see my calculations. So in the very left column, I have the various diameters, and going from 0.5 centimeters all the way to 8 centimeters. 8 centimeters is the softball hail you hear about falling in down south in Texas. And assuming that the hailstones are spheres and no air content inside, the mass can be calculated in the next column. Now, to find the velocity function, I used Newton's second law, which basically sets mass times acceleration equal to the sum of the forces. And I integrated that to find the velocity function. Then to find the terminal velocity, I just let the time t approach a very large number. And I found out that the velocity is just equal to the square root of mass times gravity over c, and c being given there. So that way I was able to find the terminal velocity of each respective diameter hailstone. And I then substitute that velocity into the velocity function, which enabled me to find the time that it would take to get terminal velocity. Then after that, I integrated the velocity function to get my distance function. And then substituting the time into there, I could get the distance that it would take to get to the terminal velocity. And as you can see in that column, the 0.5 centimeter hailstone would take 8.3 meters, but just increasing the diameter by 0.5 centimeters makes it already 17 meters to get to the terminal velocity. So as you can see, that wasn't possible it's not possible to do realistic drop tests without matching the kinetic energies. And the reason why I say 90% of the terminal velocity in my calculations is because the velocity mathematically doesn't reach the terminal velocity in finite time. So it'll only approach it, but it'll reach it only at time equal to infinity. So that's why I say 90%. Now on the left there, you can see my basic testing setup. So on the floor of the facility, I had the frame of the car built or standing. And on the right there, you can see a better picture of the frame. So I took measurements off a Dodge Caravan van, and I built a frame and then mounted car parts that I got from an auto wreckers onto there. And on the bottom right there, you can see that's a picture of the underside of the hood. Now, I tried to make it as realistic as possible, so I installed these hood supports. As you can see, the red little pieces of wood there. And actually, underneath the hood of a car, there are multiple hood supports at various locations. And I wanted to investigate the effect that these have on the damage. Now, going back to the left there, I had a column going all the way up to 8 meters, and also stairs that led to an 8-meter platform. But for the lower elevations that I had to drop from, I had to just use a ladder. And it was also convenient because the column had these bolt holes that I could just bolt the launcher, I call it. The launcher is basically just a 2x4 with a barrel on the end. And it enabled me just to drop the ice balls and steel balls I tested so that they would drop directly downwards, and I could also aim with it. If I dropped it by hand, they would sometimes veer off to the side, and it wasn't very accurate. Now on the left there, that's a picture of the chronograph I used, which was used to measure the velocity at impact. Unfortunately, it only worked for the steel balls, since the light sensors could pick up the steel balls, but they couldn't pick up the ice balls because the light would just travel through them. So, however, I did find that the velocities were more or less consistent with by using the overhead launchers. So I concluded that drop testing was going to be accurate enough for me. And then on the right there, that's a picture of the testing setup with the cover that I tested put on the hood. And I also made tests with the cover on the door as well. Now, I mentioned that I had barrels on the end of the launcher that was installed to the column, and I had 4 sizes. The largest size I had was for a 2.5-inch ice ball. The next was for a 1.75-inch ice ball. Then the next smallest was for a 1.5-inch ice ball. And then the very smallest was for a 0.75-inch steel ball bearing. And I really wanted to test the ice balls versus the steel ball bearing to see what differences in denting was. And I actually got the ice ball molds from Amazon, and they're actually just used for drinks and just for cooling down drinks. So it was nice because I didn't have to actually 3D print or manufacture any, and it worked very well. So the first phase of my testing involved making impacts with the 0.75-inch steel ball bearing. And this was done with and without the hail cover, both on the hood and the door. And like I said, I've confirmed the velocities with the chronograph. And I impacted multiple areas on the hood. The front of the hood was a little more sloped than the back, so I wanted to investigate what the difference in impact angle would do to damage. But I also wanted to investigate what differences the hood supports made to the damage. And I concluded that the door was more resistant to damage. However, I noticed that the door is of a stiffer construction than the hood. And I think that's because the door is more likely to be dented in everyday use. So that's why automobile manufacturers just make them stiffer or out of a thicker piece of steel. And unfortunately, the hail cover failed to decrease the damage for financial savings. So their claim was false. Just doesn't work. And to be specific, I tested the overlaying cover, not the hail protector, so not the one that inflates. And I also noticed that impact damage did not vary between the areas of the hood, so it was more or less the same at the front and the back and above a hood support. So I wasn't too convinced with the result. I wasn't too convinced that the hood support made no difference. So I decided to make impacts with the 1.75-inch ice ball above and around the hood support, again with and without the hail cover. And I really want to see maybe I could get different results with the ice balls than I did with the steel balls. And sure enough, I found out that the hood support did indeed have an effect. The hood support would create a local area of higher stiffness on the hood, so that when ice balls hit close to the hood support, they would break apart rather than bounce off. And when they broke apart, they would impart less damage. The dents were visibly smaller. However, ice balls hitting far from the hood support would tend to bounce off, and they would leave a larger size dent. So this leads me to believe that perhaps the solution to decreasing hail damage is a different hood support, or a better hood design rather. And in the last phase, I did impacts with 2.5-inch, 1.75-inch, and 1.5-inch ice balls. And I really want to see, specifically in this phase of testing, to see at equal impact energies if the different sized ice balls varied relative to the steel ball impact. So I did that once again with and without the hail cover on the hood and the door, and from various drop heights that would match. Some of them would match the kinetic energy of the steel ball, and the 7.9 meter 2.5-inch, the 2.5-inch ice ball being dropped from 7.9 meters equaled a real hailstone, a 1.5-inch diameter hailstone falling at terminal velocity. So I also wanted to register and see what kind of dent forms in this, or from this testing. Now, I concluded that a steel ball with similar impact energy created a sharper dent, and that did confirm that a harder object does impart more damage. However, the dent wasn't wider than the ice balls, so it didn't result in a save in money. I did find that the ice balls created more oil canning surrounding the dent, and I will show what oil canning looks like on the next slide, as well as a comparison between the ice balls and steel balls. And I also found that the ice ball diameter didn't have an effect on the damage, so the 3 ice ball sizes actually had very similar dents. And I found that the cover did not decrease damage. However, it did tend to cause some of the 1.5-inch ice balls to bounce off rather than explode. And that leads me to believe that the cover changes the impact mechanics and the stress field as well. It changed the impact mechanism to a more elastic one. And the 2.5-inch ice ball masses were the most consistent. The 2.5-inch ice balls were made in single ice ball molds rather than the tray style molds, which contributed to making more consistent masses. Now, this slide shows the at equal energies, the differences in dents between the various ice ball sizes and the steel ball. So you can see that the ice balls had very similar dents, but the steel one was clearly different. And notice the oil canning is the wavy pattern in the dent there that reflects the light. So in conclusion, you can't use ice balls to replicate, or you can't use steel balls to replicate real hailstones. It just doesn't have the same effect. And I also, near the end of my project, decided to 3D print an ice cone mold as a proof of concept. And it did end up working very well. Just filled it with water, stuck it into my freezer right side up, and on the way out, I just ran the bottom under hot water, and it popped out perfectly. So I would recommend 3D printing molds if it's needed to make ice cones. So in conclusion, the Cover King hail cover did not decrease damage for both the ice and steel ball impacts. And however, I did notice that the cover did cause ice balls to bounce off rather than explode, specifically the 1.5-inch ice balls. And I also noticed that the steel balls impart sharper dents, but they're not as wide as the ice ball dents. So fortunately, steel balls can't be used to replicate hailstone impacts. I also noticed that the door damage is less due to a stiffer construction, and hood supports create local areas of higher stiffness, which cause ice balls to explode rather than bounce off. And when the ice balls explode, there is reduced damage. And like I said earlier, 3D printed molds do work, and specifically for ice cones. And single ice ball molds are better than the tray style molds. So just a few recommendations I would have. I would develop an ice ball shooter, and I would like to see my results being compared, specifically the shapes of the dents be compared to dents from an ice ball shooter. I would like to see a method be developed to capture impact and measure impact depth. One possible tool that could be used is a laser scanner, and I know they've been used to scan different objects, and once they're scanned, they can be directly inputted into and rendered in an AutoCAD program, so you can directly measure how deep the impact depth is. However, I haven't tried that, but I would recommend trying it out. And I would perform impact tests on windshields that are installed on an actual automobile, just because making a frame for a windshield is rather hard, just because of the concave shape of the windshield. And I would recommend performing layered ice ball impacts. It seems that all ice ball impacts that have been made thus far are made with solid ice balls, but as I talked about earlier, ice balls or real hailstones are actually layered as they travel through the updraft, downdraft cycle. And I would also like to compare lab dents to real life hail dents. And ideally, it would be interesting to have a catalog that has real hail dents and approximate sizes of hail that fell that day, so we could see what the correlation is between dent size and hailstone size. So in conclusion, the hail problem is not likely to go away anytime soon. Recent demographic studies show that in the Canadian prairies in the United States, populations will continue to grow. And that means there's going to be more automobiles on the road and more damage and rising and more expensive hailstorms in the near future. And in order to solve this problem, a testing method is needed in order to qualify and test possible solutions, whether that be a new type of cover or a new hood design. And these designs need to be made in order to mitigate the hail damage to automobiles. Now, I'm very excited to see what research is going to be done in the near future and what advances towards making a testing method are going to be made. And I'd be even more excited to contribute directly into this area of research. These are my references, and I'd like to thank you all for listening to my presentation today, and I'd be happy to take questions now and have a discussion.
Great, thanks very much, Adam. Pretty interesting stuff. So first question is, so you tested only one hail protection product, is that correct? Yes, that's right. Okay, and I'm just wondering what the criteria was for selecting this product. Is it a commonly used? What's its, do you have any info on its market share in this area? Anything like that?
I did a Google search of just hail covers, and those were the two that came up. However, I haven't heard of people using that the overlaid hay cover. Sorry, like the overlaid, not the non-inflatable hail cover. I haven't heard of people use that one in London. However, I have heard of people use the inflatable one. Unfortunately, I didn't get to test the inflatable one, but I did test the non-inflatable one.
Right. Okay. And I'm just wondering about why this particular product you felt was not effective. Is it the material selected? Is it the thickness of the material? Any detail on that?
I was pretty skeptical of it in the first place, just because it's basically just like a thin little blanket that goes on your car, and I think it was just a false claim. Like, usually those kinds of covers only provide UV protection and stuff like that, but never like hail protection. So I was skeptical in the first place just by looking at it. But yeah, no, it's probably just too thin, and I don't think you can prevent hail damage just with a little blanket. It would have to be something inflatable like the other product.
Right, okay. And just a question about the marketing that's done. So this particular product that you tested, is it marketed for hail specifically, and are the claims that it eliminates damage or that it limits damage? Or is it for, a variety of, potential impacts on a car, UV, like you're saying?
They claim that it's hail resistant or resistant to light hail. But that's just like, there's no specific numbers that they say. Like, I feel like they have to say, they should say rather, up to this certain sized hail, but they just say light hail. So I decided just to test that one first, but I would like to see the inflatable protector being tested as well.
Right, and actually we have an offer online here that our product could be made available, the hail protector system, so maybe we can think about that at some point.
Okay, interesting.
A question from one of our online participants is, how do you, when you're doing your lit review, maybe you can provide some thoughts on this, but how do you think your research might help with dealing with fraudulent hail claims? So, for example, say a car owner makes dents on his car with a hammer or something like that. Would your research or similar types of research assist in identifying what hail impact should look like, and therefore help with identifying when claims are fraudulent?
Well, the testing that I did was from a energy perspective, so you could I could probably calculate how hard you have to swing a hammer for it to have a specific, or have the same kinetic energy as a hailstone impacting. But I'm just not sure how realistic that is compared to real hail, and that's an area of that has to be investigated a little further, just to see how well just matching kinetic energies actually represents real hail. Yeah, that's all I can think of for that one.
Okay, thanks. Another question is, I don't think you did consider other measures. I think you just considered this one measure, but do you think there's potential to consider other hail protection systems like canopies or netting, other tools?
I did come across a netting product on the internet, but I couldn't find a way to buy it. But I haven't heard of them being tested at all. No, I haven't.
Okay. Another question is, how can hail damage mechanics be applied to damage to say dwellings and structures like skylights, patio, glass, steel roofs, that sort of thing?
Well, there are test methods for, like I said, the windshield, like the hail resistance of windshields. There's also one for solar panels as well. And so I would follow the ASTM standard that is relevant to the product. The reason why I did this project is because there didn't seem to be an ASTM standard for body panels, the resistance of body panels to hail damage. So that's the main reason why I also did this project, just because there's a lack of that test method. And if there's a, yeah, that's all I have to say about that. Okay.
How would you, so one of the questions from one of our participants relates to how would you incorporate the consideration for wind-driven aspects that might be involved in storm-driven hail in real-life situations? So in your testing situation, it sounds like the stones or your testing impactors were dropped directly down. Is there a method that you can think of to test the impacts of wind?
Yes, I did come across downdraft-driven hail during my research, but the only way I can think of is just you have to perform some sort of calculations to see how much the downdraft increases the hail speed, and then I would just probably shoot it out of a gun at that specific speed. Yeah, you'd have to do a sort of analysis to see because different geographic areas do have different wind speeds and some have downdrafts, some don't. So I would look into that. Yeah. Okay, thanks.
Would you be able to, so you mentioned that you focused on this testing approach because there was an ASTM standard available. Getting back to that question about impacts on dwellings, could you name any standards that specifically relate to testing hail impacts on dwellings?
I believe I recall seeing one for for shingles, for testing or qualifying shingles resistance. Also saw one for solar panels, and I'll have to get back to you on that. Those are the only two I can remember.
Sorry, start again.
This is Glenn McGovern from ICLR. There is an ATSM standard for roofing. There's also an Underwriters Lab standard for roofing, such as asphalt shingles and things of that nature. Really nothing on the siding side, windows, fenestration, all that. There's a big gap in that research, but there's definitely standards for roofing.
Adam, another question about your a recommended hail damage mitigation option for automobile. You mentioned the hood supports.
Yes.
And you tested those hood supports, and I'm assuming those hood supports that you're showing in your rig there were those are typical sort of integrated into automobile design. Those are not a special design.
They're not exactly the ones used. I just kind of fabricate them myself with a piece of wood and a piece of foam on top, or a piece of rubber rather, because the ones in the car are rubber. So I just made them myself. I couldn't get a hold of. There wasn't a way I could take them out of the car, so I decided just to make them myself. Yeah.
Okay, and so just to clarify, your recommendation is to sort of increase the density of these hood supports, and that would help mitigate damage?
It's certainly worth trying just to see what effect they have. I guess that's, if I were to take my project a little further, I would look at that.
Okay. Another question about testing of hail damage to plastics, and if you can go back to that picture of that BMW that had the hail damage, it seems that the hood is damaged, but not the quarter panel. And is that because it's a different material? And so the question here is, so you were looking at steel components of automobiles. Are there different standards available for plastic components, like bumper covers, mirrors, and that sort of thing?
I did not come across that, and I'm not sure that it's a different material. The one thing I could say is that often hail comes down in like these swaths, so maybe it just missed that part of the car. I honestly don't know why it would be not damaged, but yeah, I'm not sure.
It's my understanding that hoods are made with a different material so that they crumple into an energy zone and protect the driver, and so that if the hood was made out of plastic, they would flex, then go into the cabin and kill people. So it's my understanding the hoods are made in order to crumple.
Okay.
And a question here, I guess I'm not sure if you answered the question, is there a different standard available for the different components of cars, like mirrors and bumpers and that sort of thing?
I didn't come across anything for hail resistance for those parts.
Right. Another question that's come up here in the past is the question of, so hail covers require people to physically go out of their house and install the cover. During your literature review, did you, and one of the things we know from different aspects of disaster research is that there's sort of a fatigue where people, if you continuously get warnings about weather events, and there's always uncertainty and warnings, and these weather events don't occur, after a while you might reduce your trust in these weather warnings. And so application of these covers does require information to be passed to the homeowner, and the homeowner the car owner to physically go and install the cover. Did you come across any research that indicates how likely people are to actually use these, and if use drops over time, or if there are changes in use over time?
I haven't come into contact with that sort of research. However, I would imagine people with more expensive cars or more rare cars are would be more likely to use them. I know I heard of a person at brought his car to an auto show, and he had one of those by his car. So basically, I think more rare cars where it's like kind of very big inconvenience, or sometimes like some of the parts are not replaceable. So I think in those cases, people are more likely to use the hail cover. But I didn't come across like general trends or anything like that.
Great. Okay. Thank you very much. I think one last question here. So you mentioned and you confirmed, and I understand that IBHS had also looked into this topic, the difference in the characteristics of impacts and damage associated with the steel ball versus the ice balls, and how the creation of the ice ball, or the actual physical makeup of the ice ball, affects its impact on materials. Do you have a sense that the standard developers are considering this factor and are thinking about reviewing standards approaches to say, limit the use of steel balls?
So is your question about like where steel balls are used to perform impact tests? I didn't quite get that.
Oh, sorry, no, I'm asking about what the standard developers are considering. Are they aware that their testing recommendations, like using steel balls, don't necessarily, accurately reflect damage by ice balls, and are they considering this maybe in future updates of the standards? Okay,
I see. Well, the ACM standard for windshields actually requires using ice balls. However, the reason why I wanted to prove that steel balls don't reflect ice balls is because I maybe thought that you could use steel balls. Just because making ice balls is such an inconvenience, I thought maybe you could just use a steel ball of a smaller size to replicate the ice balls. That's why I wanted to prove that disprove my the thought that you could use it. However, I don't think people are using steel balls for hail resistance. I did not come across that.
Okay, thanks very much. So I think we'll wrap it up there. Adam, do you have any last thoughts before we sign off?
No, but thank you for the opportunity to present my project. I'm really glad. Thank you.
Yeah, well, it's a great project, and incredibly impressive for an undergraduate student, I think, and I think we'll probably have you back in the future to talk about your future work as well. Awesome. So thanks again, Adam, and thanks again, everyone who joined the webinar today. And we will have a recording of the webinar available on our YouTube site, hopefully within the next couple of days, and we'll post the slides on our website as well, so those will be available. And a reminder that our next webinar will be in September, and you should watch your email for a notice from Tracy Waddington. And with that, have a great summer, and we'll talk to you again in September.